Hello viewer, I welcome you to the second episode on chemical equilibrium. In the first episode, we talked about the various aspects of chemical equilibrium, why we have to study it, and what is the mathematical formulation which can help us to have a various parameters and its relationship with chemical equilibrium. In this episode, we are going to talk about a very fundamental principle, Le-Chatelier principle, and the how to treat this Le-Chatelier principle thermodynamically. Then the temperature dependence of chemical equilibrium, that is want of factor, what is want of isotherm, and we are going to talk about the Clapeyron equation as the last part of this episode. First, we have to look at the one of the famous scientists who has brought about the effect of various parameter on a chemical equilibrium. He has tried to state that if an equilibrium is subjected to a stress, the equilibrium shift in such a way as to reduce the stress, or in other words, if a system at equilibrium is subjected to a change of concentration, pressure or temperature, the equilibrium shift in the direction that tend to undo the effect of the change. Basically, what we want to know from these statements are that if a thermodynamic equilibrium is there and we change any of these parameters, the equilibrium like to go in a direction where it can nullify or reduce the effect of the stress which is applied on the system. Now, try to look at the various parameters, how the system move when a parameter is changed. First, there is one reaction, carbon dioxide plus what H2, that gives water plus carbon monoxide. If a drying agent is added to absorb water, so the concentration of product is decreasing. So, what will the direction will be shift to right, because there is a decrease in the concentration of product. If you look at the second example, H2 plus I2 can give 2 Hi, and if we add any other gas which is not a part of this reaction, there is going to be no change in the equilibrium. If you look at the third example, the reaction is carried out in an open container. As there is a gas involved and the reaction is carried out in a open container, it shifts to the right. There are many such examples which can be quoted where a stress is applied or a parameter has changed and the system has to react to these type of external stimuli. Like water, liquid, water, gas. If water evaporates from an open container, means there is a decrease in the concentration. So, there will be a movement to the right, because it want to compensate the loss of this water molecule, and there may be such similar example where you can have a shift to the left or right depending upon the condition, but the system always moves in a direction where it can nullify the effect which has taken place. In a specific case, to stress the point which I want to stress is that if I have a Fe2 plus and HCN, it forms a complex. The color of the reactant and the color of the product are different. So, if I increase the Fe2 plus ion concentration, naturally the reaction want to compensate, the equilibrium want to shift in a direction where it can consume the excess of Fe2 plus ion. So, it will move in the forward direction as the product color is brown. So, the overall the solution will show intense dark brown color, and if increase in concentration of sulfocyanide salt, means this salt which is colorless, again it will go towards the product side because the reactant has increased, and if by any chance if we can increase the concentration of this complex, it will go in the backward direction and the overall solution will show a decrease in the intensity of color. To take an example of temperature change and its effect on the equilibrium, a very well known example of Haber's process, N2 gas with 3 H2 gas can give you 2 NH3 ammonia, which is also in a gaseous form. The enthalpy of this reaction is 92.38 kilojoule. It is exothermic process. So, when a system is an exothermic process and the change in temperature, if I increase the temperature, the system want to go in a direction where it can consume the excess energy. So, it will go in a direction in the backward way where it can consume it. So, the yield will show a decrease because more of the reactant will form. If I decrease the temperature, so the reaction will move in a direction where it can increase the temperature by expulsion of some amount of heat. So, this is exothermic reaction. So, it will move in this direction. Looking at another parameter which can undergo a change like pressure. So, how it affects the equilibrium can be studied if we take a simple example of N2O4 gas which decompose and give you 2 NO2 gas. As the number of moles of gas which is coming out can play a role on the pressure. So, we can have a look, if the pressure is increased, the system like to go in a direction where it can nullify the effect of that increased in the pressure. So, if pressure is increased, there is more number of moles of NO2 this side and less number of molecule of gas this side. So, it like to go in a direction where it can decrease the pressure. So, backward direction is favorable. When we have a decrease in pressure overall, it will like to in direction where more number of molecules are produced which result in the higher pressure. So, the forward direction will be preferred. We have to understand that if no gaseous reactant is there, we cannot have this effect seen in the equilibrium. If you try to understand the effect of catalyst on equilibrium, equilibrium is not being shifted by the catalyst. So, we can say that the catalyst do not affect the overall equilibrium and it increases the rate of forward reaction and rate of backward reaction by the same amount. So, that is there is no effect on the equilibrium due to a catalyst. If we add an inert gas, if the inert gas is added, it increases the pressure, but the partial pressure of reactant and product both increased by the same amount and therefore, the equilibrium do not show a change. On the other hand, if the inert gas is added keeping the pressure of the reaction system constant, then the equilibrium composition is affected in the case of reaction for which the volume of the product minus volume of the reactant is not equal to 0. The Haber process is the best example which give us an idea that how important or how useful this principle is. This is a standard Haber's process which can be used for the generation of ammonia industrially, and this suggests that to maximize the product ammonia, we have to use at high pressure and low temperature. This is the condition under which it should be synthesized, but to get an better yield, this too can be compromised and that is the way it is done, and this has a direct impact on the economic and social impact, and that is the reason this is the most important or celebrated law. If we try to understand the Leach-Atelier principle from thermodynamic treatment, we have to look at this equation where the reactant with a stoichiometric coefficient nu A react having A gas, nu B B, nu C C and nu D D. These are the two reactant and two product having nu A, nu B, nu C and nu D as the stoichiometric coefficient. The free energy change is going to depend upon the temperature, pressure and extent of the reaction. Extent of the reaction we have already discussed in the earlier classes. So, extent of the reaction is dependent on the delta G. If you look at differentiation of this term has to have the partial derivative of all the three terms, that is curl delta G by curl T at other two parameter constant, and when we do a partial derivative of second term of G with P and partial derivative of G with chi, which is the extent of the reaction, we are going to get an expression. This expression is already been seen where curl G by curl xi is the reaction gives free energy, and if we do a double derivative of that, we are going to represent it by G double prime. It is already known that dG is related to pressure and the temperature change by this relationship. We are going to represent the whole expression by this term, where curl G by curl T is delta V, but to represent it, it is a enthalpy of reaction, the delta R is given here, and this is enthalpy of entropy of reaction, delta R S is given. Substituting this value in the expression, we got this term d delta R G, where delta R G is the Gibbs free energy of reaction, delta R S entropy of reaction, delta R V volume change of the reaction, and this is the double derivative of the change of Gibbs free energy with the extent of the reaction. This term is represented by this. At equilibrium, we know that delta G of reaction is 0. So, the terms which contain the delta G goes away, and we got a on the left hand side equal to 0, on the right hand side we have 3 terms, and the entropy is related to the heat by temperature, where we can represent the heat by the enthalpy of the reaction, and that is seen here in place of delta R S we can write delta R H by T, and all other terms remain the same. And this is explained the G double prime equilibrium, and G has a minimum value at equilibrium. To have a minimum value, the G double prime must be positive. If you do a thermodynamic treatment of Lee-Chatterton principle, the case 1, when the chi is changing with temperature at constant pressure, we can represent it by the dP equal to 0, and there will be 2 terms remaining. The dP equal to 0 makes the dRV term disappear. So, we have left with minus delta RH by T dt at constant pressure plus G double bar d xi at constant pressure equal to 0, and when we try to rearrange the term, we are going to have curl xi by curl T at constant pressure equal to delta RH divided by T G double prime. Since G prime is a positive quantity, the sign of curl Z by curl T at constant pressure will depend upon the sign of delta H. The term here will depend upon this term, then because G double prime is a positive quantity and temperature is always a positive quantity. So, there is a direct dependency of the enthalpy on the change in extent of reaction with temperature. So, a table can be plotted where the reaction, which type of reaction we are talking about, exothermic, and enthalpy, we know that in exothermic enthalpy is negative. This term has to be positive if we change the temperature is increasing and the concentration of the reactant will increase. So, it is going in a backward direction. If we have a exothermic, the enthalpy is negative, this term curl xi by curl T is positive and change in temperature is there. So, concentration of product will increase forward. Then if you are looking at a endothermic processes where there is a positive value of enthalpy, this value is going to be negative with respect to change in temperature. If it increases or it decreases, there will direct effect on the direction in which the reactant or the product move. If you try to look at the other way possible, where xi will change with pressure at constant temperature. So, we represent the constant temperature by dt equal to 0. So, we have left with the term which contain dt disappear from the equation, and we got delta RV dP at constant temperature plus G double bar d xi at constant temperature equal to 0, and we try to rearrange this expression. In this expression, the G double prime is a positive quantity. So, the direct dependency of delta V or the volume change with the term in the bracket, that curl xi by curl P at constant temperature. So, this can be plotted if the volume of the reactant and product are almost same, there is no change, delta V is 0. So, we do not expect any change on the equilibrium, that is seen by the first line. All these terms there is no effect. If the volume change is positive, so because it contains a negative sign, it has to be negative, and the change in pressure, if it increases, shift backward toward reactant side. If delta V is positive, this term has to be negative and the pressure has to be negative or decrease, the shift towards the forward side. Negative delta V, positive curl xi by curl P, and there is a decrease in pressure, the shift backward towards the reactant side, and the same way it happens in the last one. If we know that there is a parameter which need to be understood with respect to equilibrium constant, that is temperature. So, if temperature is changing, what is the effect on the Gibbs free energy? We can look at this expression, we have already derived this expression. What we do? We rearrange the term and differentiate it with respect to temperature, because that is our aim, to understand the effect of temperature on the expression. And you can have d by dt, r is a constant. So, it has come out from the differentiation and I have left with d ln Kp by dt, and I am differentiating the curve delta g superscript 0 by t by dt. We already know that Gibbs-Helmholtz equation, this term is equal to minus delta h 0 by t square. So, we have to compare these two expression, the left hand side of both the equation is same. So, it means that right hand side has to be equal, that lead to a very important expression that d ln Kp by dt should be equal to delta h 0 by r t square. This is a well known equation known as van 't Hoff equation or van 't Hoff isochore equation. If we try to integrate this van 't Hoff equation, so that we are in position to find the equilibrium constant at two different pressure or find at two different temperature, what we can do? We can take the integration on the left hand side d ln Kp equal to delta h 0 by r, integration from the limit Kp1 to Kp2 and T1 to T2. So, this will lead to the expression 1 upon T1 minus 1 upon T2, and we can take a log of that from natural logarithm to log, and we get this 2.303. R is a universal gas constant and all the temperature are in Kelvin. So, this is a integrated van 't Hoff equation which can help you to find out the chemical equilibrium at two different temperature. What is van 't Hoff isotherm? The Gibbs free energy can change with the change of temperature and the pressure of the thermodynamic system. The van 't Hoff isotherm can be used to determine the Gibbs free energy for a non-standard state at a constant temperature, and this is expression which represent the van 't Hoff isotherm. Curl G by curl xi at constant temperature pressure is equal to delta R G, which is Gibbs free energy of reaction, plus R T ln Q R, where Q R represents the reaction quotient and this is Gibbs free energy of the reaction. So, these terms can help you to determine which direction the equilibrium is going to shift. When delta R G is less than 0, the reaction moves in the forward direction. When delta R G is greater than 0, the reaction moves in the backward direction. One of the most important equation we have for a two phase single component system is Clapeyron equation, and it is also developed by Clausius independently. So, in some cases they are known as Clausius-Clapeyron equation, and we can use the Gibbs-Helmholtz equation to derive it. What are different types of phases possible? Like you can have a water present in a liquid phase and water present in a vapor phase. So, there is equilibrium between these two, and that is going to happen at the boiling point of the liquid. The second equilibrium can be between solid and liquid at the melting point. The third possible is solid and vapor at the sublimation. There is also one more equilibrium possible between one crystalline form to another crystalline form, that is rhombic sulfur to monoclinic sulfur. Both are sulfur, but they can exist in two different crystalline form. So, the equilibrium can be between such type of systems. How to derive this Clapeyron equation? Suppose we have a pure substance A and which is in phase A, and there is another same substance in phase B at a given temperature and pressure. So, we can write G A is the free energy per mole of the substance in the initial phase A, and Gb is the free energy per mole in the final phase B. At equilibrium, these two terms has to be equal because delta G has to be equal to 0, and if we take that system is subjected to some amount of change and that change is in the temperature has gone from T plus dT. There will be effect on the pressure is also undergone a change, that is it is gone from P to P plus dP. The dP represent a very small change in the pressure. We are going to have a effect on the overall Gibbs free energy, that is the Gibbs free energy of A is going to change from Ga plus dGa, and for phase B Gb plus dGb. But as the equilibrium is already established even after the change is incorporated. So, these two terms need to be equal, and we already know that Ga is equal to Gb before it is disturbed. So, we can have a expression, that is dG equal to Vdp minus SdT for both the phases, and this term I already informed you that this two has to be equal. So, what we left with the change in Gibbs free energy for substance A and the change in Gibbs free energy for substance B, and we can write the expression Va dP minus Sa dt equal to Vb dP minus Sb dt. Try to rearrange the term so that we can get dP and dt on one side. So, we are going to get this expression dP by dt equal to the change of entropy of B minus entropy of A, volume of B minus volume of A, and this can be written as the delta S by delta V because they represent the final minus initial. It is already known that delta S is equal to Q reversible by T. So, when you plug in these values in the Clapeyron equation, we are going to have dP by dt equal to Q reversible by T. In place of delta S here, we have Q reversible by T and delta V was already there. So, this is well known Clapeyron equation. When we have to talk about a single component two phase system, we have to use this expression. We have to get it at two different phases. Look at the different cases which is possible, like water can exist in two different phases. We can have the change in pressure with change in temperature, and this represent the enthalpy of vaporization, and this is V gas minus V liquid, and these two are G is going to represent the gas, L is going to represent the liquid, and this is the expression which we got. We want to have a integrated form of this expression. At freezing point, we are going to have like delta HF, that is molar heat of fusion of ice, and the expression remain the same. The final, that is a liquid minus solid. The integrated form can be obtained if we assume that in the denominator the V gas minus V liquid, the gas is very high or very large in volume as compared with the volume of liquid. So, we can safely neglect this V liquid and keep only the V gas, and this is a modified form where the liquid term is removed from the denominator, and this can be easily be integrated, and we have to use the ideal gas expression where Pv equal to RT for 1 mole, and when we put these values here, V which is a gas, RT by P, there is going to dP by dt equal to delta H V vaporization, molar heat of vaporization by temperature, and the V gas is replaced by RT by P. So, it has to go in a reversible manner. So, P by RT, and we got a expression P delta H V by RT square, or we can rearrange the term, the P is cross multiplied and we can carry out the integration with limits. So, the pressure can change from P1 to P2 dP by P, and the temperature is going from T1 to T2, and this can be written in the natural logarithm ln P2 by P1 equal to, this term is going to give minus 1 upon T, and when we put the upper and lower limits, I have taken out the negative sign, but in the final expression this sign has incorporated inside, and that lead to the expression. This is the integrated form of Clapeyron-Clausius equation, and natural logarithm has been changed with the log. If you look at the application of Clapeyron-Clausius equation, the first application which can be thought about is the calculation of molar heat of vaporization, and if the pressures are known, we are in position to get the temperature and vice versa. If the temperature are known, the pressure can be calculated using the integrated form of Clapeyron-Clausius equation. We would like to take another case of a simple system, solid vapor, where there is equilibrium and the V gas and V solid. We know that this solid volume is negligible as compared with gas. So, it can be treated in the same manner for liquid gas, and we can get the similar Clapeyron-Clausius equation, but remember that this is the delta H of sublimation. But in the third case, where solid liquid are there in the system, they cannot be integrated easily because the volume of solid cannot be neglected with respect to liquid. So, they have to be used in this form with both the volume together. If we look at one numerical to understand it better, if we have a ether which boils at this temperature at 1 atmospheric pressure, we have to find out the temperature at which it boils, and when the pressure is 750 mm, the heat of vaporization is given. So, we can use the integrated form of Clapeyron-Clausius equation. If we try to look at the solution of the numerical, we can get it from the integrated form of Clausius-Clapeyron equation, and there is a pressure terms which is there P 2 by P 1, and the delta H V, delta heat of vaporization term which is in grams. So, it has to be converted into mole, and only unknown we have is the temperature which has to be determined, and if we solve this numerical, we are in position to get log T 2, and after solving the T 2 we get a temperature that is 634.3 Kelvin. This completed the topic, and in today's lecture we have discussed about the Le-Chatelier principle, the thermodynamic treatment to obtain the Le-Chatelier principle, how it can be governed, and the temperature dependence of equilibrium, that is van 't Hoff factor, then reaction isotherm and Clapeyron equation and the various types of Clapeyron equation. Overall, we in these two lectures we got information about the chemical equilibrium, how chemical equilibrium can play a role, how this can be controlled for application, and what are the different types of chemical equilibrium we have. So, I hope you will be able to understand and appreciate the reaction which goes towards to and fro and equilibrium exists in them, and how to manipulate it to control these type of equilibrium processes. Thank you.